my rabbit and I have decided to leave planet Earth. Isn't that right, Bambi? And I'm sure everyone shares the same sentiment. So today I'll be showing you the physics and the mathematics behind calculating the escape velocity of the surface of the Earth. First, let's answer this question. What is escape velocity? It is the minimum speed required to get off the surface of the Earth so that it can overcome Earth's gravitational pull. Basically, Newton's law states that every single body in this universe is attracted to each other. The more massive the body is, the more attractive it is. In our own solar system, Jupiter has one of the highest gravitational forces that we know of. But it has an inverse square relationship, which means that as we get away from planet Earth more and more, the less of the force of gravity we experience. There is less attractive force between the two bodies. So if we were to plot the force against distance, we would get this kind of relationship. As the distance between the two bodies increases, force that we experience becomes less and less and less. Technically, we still experience it no matter how far away we are. So even if we're millions of kilometers away from Earth, we still do feel a force of gravity. It's just very, very, very small. So small we usually say it's almost zero. I'd also like to highlight that there is a difference between the force of gravity and acceleration due to gravity. Myself as a lecturer, I see that students mix up these two concepts. And I think it comes down to the fact that we loosely call everything gravity. Gravity can mean Einstein's gravity theory, it could mean Newtonian's gravity theory, it could mean weight, or it can mean the G value, the 9.81 meters per second squared that is on the surface of the Earth. Which one is gravity? All of them. It just depends how you fill in the sentence. Generally speaking, gravity is referred to the force of gravity. In classical physics, we refer to this as Newton's law of gravity. F is equal to G times mass 1 times mass 2 all over the distance squared. Sometimes loosely, we refer to gravity as the acceleration due to gravity. We usually note it as a lowercase g, and that is 9.81 meters per second squared on the surface of the Earth. That means if I drop anything, I always look for something to throw or drop in my lectures, I swear. If I drop this rock with a really cool fossil, it means that every second its speed increases by 9.81 meters per second. Hence the unit meters per second, or meters per second squared. The acceleration due to gravity is due to the force of gravity. It is not referred to as gravity itself. Sometimes, however, loosely in the English language, we might refer to that as gravity. Hence the confusion. One is the force of gravity, F is equal to ma, or F is equal to G times m1 times m2 squared. And the other one is just lowercase g, the acceleration due to gravity. Make sure we know the difference between these two. All right, now that we have all the basics, let's get off the surface of this planet. Here is a very accurate representation of planet Earth. And this right here is you. Not drawn to scale. R represents the radius of Earth, and X is some distance off the surface of the Earth where we would like to get away. This is the kinetic energy of U, the mass, that is required to get off the surface of the Earth with the escape velocity VE. Let's start with Newton's force of gravity. G is a gravitational constant. It's just a universal constant that we need to use to adjust our numbers. Lowercase m is your mass, capital M is the mass of the Earth, and X is the distance between you and Earth. So what do we need to do? We need to put work into getting off the surface of the Earth. The equation for work is force times distance. Now, we're doing a little thing here where we have dw dx. Sub in the value for f from the above equation. This is our final expression. Our limits for integration are going to be from r to infinity, because we're starting from the surface of the Earth and we're trying to get as far away possible. What's the furthest thing possible away? Infinity. Now, what does this integration really mean? Well, we have a bit of a problem. The work required to get off the surface of the Earth isn't just a constant value. It actually changes depending on how far away from Earth we are, because the gravitational pull of the Earth is changing because we're increasing the distance between us and Earth. So each time we get further and further away, the work required takes less and less. And that's exactly what integration really does. We're taking tiny, tiny increments of the distance, calculating the work required, and adding them all up together between r and infinity. I won't go through the calculus of this. If you need a little bit of help here, I advise going through Introductory to Calculus and Integration. So we ultimately get minus gravitational constant times the mass of the Earth times the mass of u all over 1 over x, where x has the limits of infinity to r. That becomes 1 over infinity minus 1 over r. 1 minus infinity, what the heck is that? Well, think about it. Infinite means super, super, super big. Flip it the inverse. 1 over a huge number. It's so big that we pretty much approximate it to 0. Hence, this becomes 0. I hope I have not offended too many mathematicians here. Inside our bracket, we're just left with minus 1 over r. The two minuses will cancel, and so we get the gravitational constant mass of the Earth, the mass of you, all over the radius of Earth. All right, we need to put that amount of work into getting us off the surface of the Earth. Well, we're going to transfer it all as kinetic energy. The way to get off Earth is by putting energy into our movement. Half mv squared. Let's equate those two guys together. The two m's cancel, your mass. Rearrange the equation to find the escape velocity to be equal 2 times gravitational constant times the mass of the Earth all over the radius. This is a pretty good equation. We can sub in values already if we wish, but we can get it down simpler. When we're on the surface of the Earth, we have a force of gravity that we're experiencing. Weight is equal to mg. And we can equate it to Newton's gravitational force. The two m's cancel. We can rearrange the equation to find the acceleration due to gravity is equal to the gravitational constant, the mass of the Earth, divided by the radius squared. If we move one of the r's up here, this looks familiar. We have that exact relationship here, and we could sub it in. Ta-da! We have the escape velocity. The escape velocity is equal to root 2 rg. We know what the radius of Earth is. We know what the acceleration due to gravity is on Earth. Sub in our values, we get that the escape velocity is 11.2 kilometers per second, or 11,200 meters per second. I'm so sorry I don't know imperial, so I'm not even going to mention it. So the conclusion of the video is really, really cool. It means that to overcome the gravitational force of Earth, you need to yeet yourself off the surface of the Earth at 11.2 kilometers per second. That's really, really fast. But what's really cool is that it is mass independent. It means that it doesn't matter how much you weigh, whether it would be just yourself or a spaceship or anything like that, you all have to reach 11.2 kilometers per second. Just to highlight a misconception here, it doesn't mean that it doesn't require more force to get a bigger object off the surface of the Earth. For example, a really, really heavy spaceship is going to require more force. F is equal to ma. That m is going to affect the force required to launch your big spaceship versus a small spaceship. But the velocity that it needs to achieve remains constant. I hope you enjoyed this video, and I wish you luck in getting off the surface of the Earth. It's a scary world we live in these days.